I'm going to talk about EKR theorem for groups. I can see everybody's face and I've got the chat up. So if you have questions, you can either wave or put it in the chat. I can see them both. I'm going to present a whole big bunch of joint work with a lot of different people, and I'm going to try and give an overview of the whole problem of EKR theorems for groups. I'm sure I'm going to leave stuff out, but we have lots of other speakers who can fill in the gaps of the stuff I leave out. Okay, so everything's good. You can hear me, see me. Okay, and let me know if there's any problems. Okay, hang on. Let me see if I can turn the page. Ah, perfect. Okay, so I'm going to start with the definition of what I'm talking about. I'm looking at a permutation group. So I've got a group and there's an action that the group has. What I talk about is two permutations being intersecting if there's some element that they both map to the same spot. So two permutations, sigma and pi, are going to be intersecting if there's some I that they both have the same image. So a permutation is called a derangement if it has no fixed points. So if we have two permutations that are intersecting, if I take one and multiply it by the inverse of the other, that will have a fixed point. So this guy's fixed. And so derangement is when you have no fixed points. So two permutations are going to be intersecting exactly when one times the inverse of the other is not a derangement. And what we're going to be looking at is for sets that are intersecting. So if I have a big pile of permutations, I say that set of permutations is intersecting if any two from that set are intersecting. Okay, so the big question has to do with what's the size of the largest set of intersecting permutations in a group? And then the next part, once we know the size, is what's the structure of the largest set of intersecting permutations in a group? So my plan is to go through a bunch of the different tools that we can use to prove these results, and then talk about what we know. Okay, one thing that's really we have to watch is I talk about this as a property of the group, but there's a group action. And obviously intersection depends on what action you're talking about. So I'm concerned more with transitive groups. I want a faithful action, so I don't have two permutations that map everything to the same spot. The intersection depends on the group action, and usually you'll consider common group actions like the symmetric group acting on the elements 1 to n, or you could think about the symmetric group acting on ordered pairs, so sort of natural actions you'd think about. But anytime you have a transitive action, so for any transitive, let's try this. Oh, I picked up purple. I thought the color went well. Oh, purple highlighter. Okay, anytime you have a group action, you can find a subgroup so that the action is equivalent to the action on the cosets. So most normal people think about these natural actions, but mathematicians will generalize it so that you have a group acting on cosets. Okay, so if I've got a group acting on cosets, if I have a fixed point, so if an element of my group has a fixed point, it moves a coset, it keeps a coset in place. And you can only get that if your element is conjugate to something in your subgroup H. So we can write down what the set of derangements are. They're everything that doesn't fix a point. And you can see Berstani and Malahai-Kari noted that if we're an intersecting set, so S is going to be an intersecting set, so I'm going to take all the elements in S, multiply them by inverses of elements in S. Everything in there has to have a fixed point because it's intersecting. So it has to be contained in this, this union of conjugates of H. One thing that you can note, obviously H is going to be an intersecting set. And if H is normal, then this is a really easy thing to work with. If H is normal, when we take the cosets, we only ever get H back again. So we can see that any intersecting set is going to be a subset of our H, and everything is pretty clear what happens then. Okay, so throughout this talk, because this workshop's supposed to be about open problems, I try to have orange open problems every couple pages. When we have an H, when do we have a subgroup in here? There are interesting examples where this union contains a subgroup other than H, and it's sort of interesting, and it brings up this sort of group property that's interesting to think about. Okay, if I have an intersecting set, I can multiply it by any element in G, and it's still going to be intersecting. So I can always assume that any element is in my set. Usually you pick the identity to be in it. If I have a subgroup, and now this time I'm looking at a group, not just a set. If I have a subgroup and every element has a fixed point, then that subgroup is going to be intersecting. And that's easy to think about. If I pull any two permutations from my set, I multiply one by the inverse of the other, that's still going to be in S. And because everything in S has a fixed point, it has a fixed point, so they're intersecting. So my favorite intersecting sets, I call them canonical. They're sort of like the obvious candidate for a nice big intersecting set. So I define it as Sij. So the set, oh, you know what? I shouldn't have written it like this. I knew I'd find typos. I'm going to put this for any group here rather than S, just the symmetric group. So for any group, I can define this Sij. They're all the permutations that map I to J. Obviously, they're going to be intersecting. They all match at the point I. If I and J are the same, it's the stabilizer of a point, which is a really nice group. If they're different, it's the coset of the stabilizer of a point. Ah, drat, look at this. This is the number for the symmetric group, but if G is transitive, what we have is the size of G divided by the size of the set it's acting on. So we know exactly its size. And I'm also going to use Vij for the characteristic vector. So the characteristic vector is going to be a vector the length, the size of the group. The entries are going to be 0, 1. I'll put a 1 for every group element that's in my set and a 0 otherwise. So the Vij is the characteristic vector for this. Okay, so I've got these beautiful canonical intersecting sets. One of the key questions is, when are the canonical intersecting sets the largest intersecting sets for a group? So I've defined a bunch of properties. The first one's the EKR property. It has to do with the size. So I'll say that a group, and I should be a little careful, I'm lazy and I keep saying a group, but the group has to have an action. So a group action has the EKR property if the size of the largest set of intersecting permutations is the size of the stabilizer of a point. And I said a largest stabilizer of a point, but mostly I just think about transitive groups, so that doesn't matter. So my cat's already at the window, drawing its claws down the glass. It is a lovely sound. Okay, so that's the first property. The EKR property has to do with the size. I'm going to jump to the strict EKR property. A group action has the strict EKR property if the only maximum intersecting sets are the stabilizer of a point or the coset of one. So the EKR property, the canonical are the biggest. Strict EKR, the canonical are the only maximum. And then there's a property in the middle that I quite like. What happens is, we talk about the EKR module property. If we take an intersecting set, and I'm going to write down its characteristic vector, if that vector is a linear combination of these Vij's. So I'm going to take the characteristic vectors for my canonical intersecting sets, I'm going to take the span of them, and I get a whole big vector space. It's actually going to be a G module because G will act on these vectors and it will keep within keep within V, which is why I call it a module property. So if the characteristic vector of any maximum intersecting set sits in this module, I say it has the EKR module property. And what happens is, if you have this property, any maximum intersecting set, the characteristic vector of it is going to be a linear combination of the Vij's. So it's not quite a characterization, but it's sort of along the way. Okay, so I've got the three properties about the size, a sort of thing about the structure, and knowing exactly the structure. So my favorite way to look at these is using a thing called a derangement graph. If I have any group, I can make the derangement graph. I write it as gamma G. The vertices are the elements in my group, and I do the adjacencies by whether or not they're intersecting. So two vertices, so two elements in the group, are going to be adjacent if and only if, when I multiply them out one by the inverse of the other, I get a derangement. So I've defined this graph exactly so that permutations are adjacent if they're not intersecting. And so the way I've set it up is now I'm looking for the largest co-clique, or the largest independent set in this graph. Okay, so an intersecting set is a co-clique here. Here's a couple of examples. If I have an n cycle and I take the subgroup generated by the n cycle, my derangement graph is just going to be a complete graph. If I have a group that's generated by sigma and I can then, okay, so if I have a group generated by a single permutation, I can figure out what the derangement graph is by the length of the cycles in the sigma. So here I did it for 1, 2, 3, 4. So if I start with the identity, well, it's going to be adjacent to the things that are derangements. And then for every time I take a cube or a square of this, I'm not going to get an edge because they're going to be intersecting. So I can actually write down the derangement graph as the complement of a circulant graph. So the derangement graph, it's got this really nice structure. So the circulant graph where the edges are just decided by the lengths of the cycles, and then we just take the complement. Does that make sense? The orange edges are the edges we don't get because squaring, we either have 4 going to 5 or 4 going to 4. The red edges are the edges we don't get because when we have 1, 2, 3 and we take powers of 3 of that, they'll have intersections. If I take a product of groups, so if I do an internal direct product of two groups, I can just write down the derangement graph as a direct product of derangement graphs. So it has this really nice structure. So one open question I have is, what about other graph products? Are there other natural graph products, other interesting group products where we can figure out the derangement graph using graph products? Okay. One of the best things about the derangement graph is that it's a Cayley graph. And even better, it's a normal Cayley graph. So when we have a Cayley graph, we have a group and a connection set. So what's going to happen is that the vertices are the elements of the group, and the connection set decides when two elements of the group are going to be connected. So two elements in G are going to be adjacent in the Cayley graph if one times the inverse of the other is sitting in the connection set. So here the connection set is exactly the set of derangements, which is why we call it the derangement graph. Now the set of derangements, that's going to be closed under taking conjugation, right? And what happens is that the set of derangements is actually a union of conjugacy clauses in the group, which gives it some really extra special nice structure. We have also, I'm not going to go into the definitions here, although many people are big fans of association schemes. The derangement graph is a graph in an association scheme. It's a really well-known, understood graph association scheme. That means that when I take this graph and I write it as a matrix, there's all sorts of good algebra sitting, waiting, ready to be used. Okay, one thing that's funny is when you make a graph, the first thing you ask is it connected? This graph is going to be connected exactly when the derangements generate the group. And this, as far as I understand, it's a hard question in group theory. There's like a recent paper that appeared where there were, I think it was Rosemary Bailey and Peter Cameron were, and some other authors were like figuring out new conditions and new results about when the set of derangements generate the group. So it's a hard problem. And it's funny that this graph, you know, asking is it connected or not is related to this very difficult group theory problem. So I put this one as an open question. I don't recommend trying it, but maybe reading about it would be good. So for which groups does the set of derangements generate the group? And I think most groups, the derangements generate the group, but not always. Okay, so when we're holding on to a normal Cayley graph, we can actually get the eigenvalues of the graph. I'm assuming everybody knows what I mean when I say eigenvalues of the graph. I take the graph, I write it as a matrix, and I do the eigenvalues of the matrix. And when we say normal, we mean like a normal subgroup, meaning when I take it's closed under conjugation. Oh yeah, for Cayley graphs, there's two definitions of normal, right? What I mean is that the connection set, this guy, is closed under conjugation. Okay, good. Okay, when I'm holding on to my normal Cayley graph, I can calculate all of my eigenvalues of the graph using the irreducible characters of the group. So for each irreducible character, I evaluate the character on the elements of the connection set, and then I have to scale by the dimension of the character, and that will give me the eigenvalues. So for each irreducible representation, I've got an eigenvalue. There's a corresponding G module, which is like I think of it as the eigenspace, but that's not quite right, because you could have two different irreducible representations giving you the same eigenvalue, and the two modules together would be the whole eigenspace. And we also have a projection to the module. And one thing that's funny is that when you go to the symmetric group, in some sense, the irreducible characters of the symmetric group are completely understood, but there's kind of a lot of them because they correspond to integer partitions of n. So we understand what they are, but calculating the actual eigenvalues is a little bit difficult. But Koo and Wales have a paper where they point out a lot of interesting patterns that happen between the eigenvalues, like which character gives you the largest eigenvalues with certain conditions, or repetitions or patterns between the eigenvalues. And there's some really interesting stuff in there. Okay, so in terms of tools, one of the most basic tools that I would use is the clique-co-clique bound. It's sort of like plan A for any group. Anytime you're holding on to a group and you're like, is this EKR? Trying a clique-co-clique bound is the easiest. So if we have a graph, I wrote it as a graph in an association scheme, but if your graph is regular, that's going to be good enough. We always have that alpha x, omega x is less than or equal to v. So this alpha is the size of your max co-clique. And then clique. Omega is the size of your max clique. And the size of the two of those, when we multiply it up, can't be any more than the number of vertices in your graph. We also know that if we have equality, then if we have a maximum clique and a maximum co-clique, the intersection is going to be equal to 1. And it makes sense that the intersection can't be any bigger than 1, because 1 is a set where everybody's adjacent and 1's a set where nobody's adjacent. So 1's obviously the best you can get, but when you get this bound, you get exactly 1. But like I said in the previous slide, for every irreducible representation, we get an eigenvalue, a module, and projections down to those modules. What happens is that if we have the clique-co-clique bound holding with equality, if I take a maximum clique, a maximum co-clique, and I write out their characteristic vectors. So this is the characteristic vector for a max clique, characteristic vector for a max co-clique. When I project those down into my different modules, one of the two has to be 0 at least. They could both be 0, but one of them is going to get squished. So the way I think of it is that we have these modules and we have these characteristic vectors of our cliques, co-cliques. They can't both live in the same module. So when we project them down to one module, one of them is always going to get, the projection is 0. Yeah, so they don't play nice together. They don't share the modules. Okay, here's an easy example with the clique-co-clique. If I'm holding on to the symmetric group and I make its derangement graph, it's going to have an n clique. So if I just take the cycle 1 up to n, take the subgroup generated by that, that's going to be a clique. And that tells us that the maximum co-clique in the symmetric group is no bigger than the number of vertices divided by the size of the clique, n minus 1 factorial. So this is exactly the size of our canonical guys. What this tells us is that the symmetric group has the EKR property. We've got the size right away just by holding on to this subgroup for the symmetric group. And whenever we have a sharply one-transitive group, a sharply one-transitive group is going to be exactly a clique in our derangement graph because it has enough group elements to map everybody somewhere, but because it is sharply one-transitive, every time we've got an I going to J, there's only one permutation that's going to do that. So every time you have a sharply one-transitive group, a subgroup, the group has the EKR property. So anytime you get a group and you're wondering, could this be EKR? Just look for sharply transitive subgroups as the first easy thing to check. Okay, this was I think first written down by Deza and Frankel. I don't remember the year, it was a long time ago, before my time. So this was known ages and ages ago. There's a little bit more that you can do with this, that the symmetric group has these nice, easy, big one-transitive subgroups, but it actually has a lot of one-transitive subgroups. It actually has a lot of one-transitive subsets. So what we can actually do is every time we have an irreducible representation, except the N1, which is the trivial representation, and except this special one, there's a sharply transitive subgroup so that the projection is not equal to 0. So the symmetric group has so many cliques, we can grab these cliques and project them down to the different modules, and every module, but the trivial and the n-1 module, we're going to be able to find a subgroup so the projection is not 0. And so because the cliques and co-cliques can't share modules, that forces every co-clique, every maximum co-clique is going to sit in the trivial module and this module. What this actually tells me is that the symmetric group has the EKR module property, that I can take all of these cliques and show that all of the modules are forbidden to the maximum co-cliques, except for the trivial and the n-1, and it's really easy to show that the characteristic vectors of our canonical guys, these span this module and the n-1 module. Okay, so this is a proof that I've only seen for the symmetric group. Is there some sort of group property that would imply that there's enough big cliques to be able to use this method to show the group has the EKR module property? So say we know we've got a clique, and then our automorphism group is huge, maybe we can move that clique around enough so that we get lots and lots of cliques and could prove something similar. I don't know. Wang and Zhang did a proof that they showed the symmetric group has the strict EKR property. And I think they win the prize for the shortest proof that the symmetric group has the strict EKR property. And what they did is they kept pulling out different cliques and showing this, we've got the clique co-clique bound. So any clique and maximum co-clique intersect in exactly one permutation. And they just kept pulling out different cliques and they forced a structure on the co-clique. So could their approach be applied to other groups where you have lots and lots of cliques? They also showed in a follow-up paper that the Coxeter groups of types SB and SN have the strict EKR property, provided that your n is, I think, greater than 3, so not a particularly strong restriction. Okay, so that tool was the clique co-clique bound. There's another tool that we can use, graph homomorphisms. So if we're looking at a vertex transitive graph, we can see what its fractional chromatic number is. It's just the size of the group divided by the size of the maximum co-clique. So I guess I'm making it sound like, oh, that's so easy. You still have to figure out the size of the maximum co-clique, which is, NP hard and all, but pshaw. If there's a graph homomorphism, so by graph homomorphism, I mean a map from the vertex set of one graph to the vertex set of the other. And what I want is that if I have two vertices back here that are adjacent, they have to be taken to adjacent vertices. If they're not adjacent, I don't care what happens to them. So it's much weaker than an isomorphism. So if I can do a graph homomorphism from a little graph to another, from one graph to another, what I can actually get is the fractional chromatic number of the first one is bounded by the fractional chromatic number of the second one. Okay, and so what I can do is that if I have a graph homomorphism from gamma of h to gamma of g, the fractional chromatic number of the h, which is this guy, is less than or equal to the fractional chromatic number of the g. And this inequality I can rewrite as a bound on the co-clique of the big guy, of the guy you're going into. So if we have a situation where I've got a group and I've got a subgroup, and the subgroup is transitive, and if the little guy is transitive, the big guy is going to be transitive. If the little guy has the EKR property, then the big group has the EKR property. And I can just do that with the graph homomorphism. I can take my little guy into the big guy. I'm just doing a simple embedding, and then I can get a bound on the size of the maximum co-clique of the big graph. And when I rearrange it, it's exactly the size of a stabilizer of a point in a transitive group. We can actually push this a little bit further. This is something that Spiga did ages and ages ago. If our group, if we have the same setup where we've got a big group and a little guy, and the little guy is has the strict EKR property, now here we need something extra. We need the little guy to be two-transitive, not just transitive. So if the little one has the strict property, the big group has the strict property as well. Okay, so my open question here is how can we use this with other groups? So if we have H as a subgroup of G, it's pretty easy to do the homomorphism. You just embed it. But I would like to see an example where you could get a bound on the co-clique of a big guy with some other type of homomorphism. So this H doesn't have to be a subgroup. It could be any other group. It could be a group that we just know its EKR-itness easily, and then we can apply it to G. But I don't think I have any examples where this works. And I also was hoping like this group down, this graph right here, you know, I put it as a derangement graph because it's easy, but it doesn't have to be a derangement graph. What if I took, I don't know, it doesn't have to be a derangement graph. It could be any graph that I understand well. Okay, so that was the last. So we've got the clique co-clique bound, we've got the homomorphisms, and now I'm going to use Hoffman's ratio bound. This debate about what the name should be for this. Should it be Hoffman's? Should it be Delsart's? Should we like skip putting someone's name on it and just call it the ratio bound? I don't know. I guess we could have a big intense discussion about that later, what it should be called. So if I'm holding a D regular graph, so I've got a graph, every vertex is degree D. I can get a bound on my co-clique where I take the size of the vertices and I divide it by this number right here. This guy is my degree. And this little tau is going to be an eigenvalue, but I want it to be the least eigenvalue. Eigenvalue, least. So what happens is that what pushes this bound is the ratio between the highest eigenvalue, the degree, and the least eigenvalue, the tau. So it gives me a nice bound. If equality holds in the ratio bound, I can get a little more information. So if this holds with equality, then I can get information about the characteristic vector of a maximum co-clique. So if I have a characteristic vector of any maximum co-clique, what's going to happen is that it's going to be an eigenvector. So I've got two eigenvalues going on here. I've got my degree and my tau. The characteristic vector is going to be an eigenvalue for the tau, but I have to do a little adjustment. Because it's an eigenvalue for tau, it has to be orthogonal to the eigenvector for the degree. The eigenvector for the degree is going to be the all ones. So what I'm doing here is I'm taking my characteristic vector for the maximum co-clique, and I'm going to make it orthogonal to the all ones vector. So I'm just doing a good old Gram-Schmidt process. And now this thing is going to be an eigenvector for tau. And that can give me information about the structure because it puts the vector in a module or a vector space.
Karen.
Yep.
You have a question in the chat.
Oh, so I didn't even see that one. Two-transitive is known to be not. Oh, Mike is asking on the previous one. This one, if you've got two, this theorem, right?
Yep.
I would say no, because you could have two groups that both have the strict EKR property and neither is two-transitive.
I guess what I'm asking is, if you are there known to be examples where it's not two-transitive and it fails?
Oh, okay. So where you're not two-transitive, this one has the strict and this one does not?
Yeah.
I have no idea. That's a great question. Okay. So here as a sub-question, oh, can I put this in orange? Orange is the question color.
Okay.
Is this needed? Is this necessary? Let's just go needed. Or could we change it to something else? What would be a more general statement here?
Yeah.
Okay, that's good. Thank you. Usually with the chat, a little red dot comes up, but I didn't see it this time. Okay, so what were we doing? Hoffman's ratio bound. Oh yeah, here's a really easy example with it. Frobenius groups. When you're holding on to a Frobenius group, the characters are totally known, and it's actually really easy to calculate the entire spectrum of the derangement graph. And the spectrum is n-1, the degree with multiplicity k, and -1 with this multiplicity. And so you can see exactly what the graph is going to be. The graph is going to be a union of k copies of the complete graph on n vertices. So this is the nicest graph you're ever going to come across. I can tell you exactly what all of the code-cliques are. We just take one vertex from each component, and it doesn't matter which vertex we pick. So there are n to the k maximum code-cliques. So that's just by counting the number of code-cliques. If my k is bigger than 2, it's not going to have the strict EKR property. But what I can do is I can figure out the eigenspace for the eigenvalue -1 and its dimension. It's right there, right? I can see it. I can take these VIJs, these characteristic vectors of the canonical code-cliques, and I can show that they span the entire eigenspace where the eigenvalue is -1. So by the ratio bound, I know that my maximum code-cliques have the right size, and I know the characteristic vector of any maximum code-clique is going to sit, when I shift it, it's going to sit in the -1 eigenspace. But I also have that these VIJs are a spanning set once I shift them for the -1 eigenspace. So I can actually pull out of this that the Frobenius groups have the EKR module property just by looking at the eigenvalues. And Pentangi, who's going to be speaking on Thursday or Wednesday, I haven't checked the schedule enough. He has another proof that every Frobenius group has the EKR module property. Okay, so the ratio bound shows us that the Frobenius groups have the EKR property and the EKR module property. The strict only when our k is small enough. Two-transitive groups are sort of my favorite of these guys. If we're transitive, we know the size of the stabilizer of a point. We can pull out this character. I never know what to call this. I'd say the permutation character minus the trivial character. What I'm going to do is pull out an element of my group, calculate its number of fixed points minus 1. That's the permutation character minus the trivial character. Now here's what's nice. If my group is two-transitive, no, I should say it this way. My group is two-transitive exactly when this character is irreducible. So the group is two-transitive if and only if the character is irreducible. And you can actually just take the character, multiply it by the inner product with itself, and then you'll get equations that look like Burnside's lemma. If it's two-transitive, things come out to 1, and so it's irreducible. Okay, so this is fairly straightforward to see. So what happens is when I'm two-transitive, I have this really nice character because the character has to do with how many fixed point my elements have. So when I'm two-transitive, I'm going to pull out this character and I'm going to use this character to figure out what its corresponding eigenvalue is. So if I have this set of derangements, I figure out the eigenvalue for this character, and wow, I get this pretty little number. So the character corresponding to this irreducible representation is the number of derangements divided by n-1 with a negative. So for sure, this is going to be an eigenvalue for any two-transitive group. If magically everything's perfect and it's the least eigenvalue, I drop it into the ratio bound and exactly the right number falls out. So if this is the least eigenvalue, I've got the EKR property with the ratio bound. So the open question here is, for which two transitive groups does this character actually give you the least eigenvalue? And it's lots, but not all, some. There's also something weird. If your group is one transitive, then this character, this fixed points -1, is not irreducible. So you're not going to get an eigenvalue from it. But sometimes in examples, this guy shows up anyways. I don't know what's up with that. So when one transitive groups like sneak around and have this as one of their eigenvalues too, I think there might be something curious. There might not be, I don't know. Open problems, so. Okay, so we can apply this for the group PGL2Q. The character table for this guy is completely known. We can calculate the characters, the eigenvalues can be calculated. So I can calculate my eigenvalues. This guy right here is my trivial. It's giving me my degree, so it's a big positive number. And I have these two little characters that give me the least, and I've got this negative number. So if I take these guys and I drop them into my ratio bound, I get the right number. And Pablo Spiga and I did this a couple years ago. It's going to have the EKR property. But there's something sort of sneaky going on in here, right? I have two different irreducible representations giving me the same eigenvalue. Now I think this is the one that I like. This is my number of fixed points -1, and this is a sneaky little guy that's getting in the way. We can actually tighten up our ratio bound a little bit. Let's go back. Oh, did it go? There. This little guy, it's a character I can figure out. It's the character that comes from taking the trivial on a subgroup, so the trivial character on PSL, and inducing it up to PGL. So this is a character that takes one value on PSL and a different value on each conjugate, it gets a different value. It's a character that's constant on the cosets of PSL. And what I can actually do is I can say I've got this nice big intersecting set in PGL. I can actually show that it's going to be evenly distributed between the different cosets of PSL, because it has to, well, I can show it's evenly distributed. And then this character, when I sum up the value of the character on the different cosets, it always adds up to 0. So by looking at this character sort of carefully, I can see that any maximum co-clique evaluated, like when I try to project it down to this module, it's always going to get squished down to 0. So using information about the irreducible representation, I know what it's going to do to any maximum co-clique. So I can actually tighten up my ratio bound a wee bit. So the formula I have here is exactly the same as the old ratio bound. And before, what I said is I take, let this guy be the least eigenvalue. Before it was just take the least eigenvalue and we stop. But we can actually throw away the irreducible representations that I know will squish every maximum co-clique. So I take the least eigenvalue over all irreducible representations, which this thing is not equal to 0 for S, a maximum co-clique. So if there's an irreducible representation that I know will take this thing is always equal to 0, I don't have to worry about its eigenvalue anymore. And that's what happened with the previous case. I had a representation, a module. I know that none of my co-cliques are sitting in that module, so I don't need to include it in my list of eigenvalues where I need to find the least. And this is like what we do with the clique-co-clique bound. When we had equality in the clique-co-clique bound, if we had a module that was holding that a clique sat in, no co-cliques can be in that module either. So I don't care what eigenvalue that corresponds to that irreducible representation. I don't need to include it in my ratio bound. Okay, so this is what Spiga and I did. We showed that we have the EKR module property. What we were able to do is show that sneaky irreducible guy we don't care about. We can throw him away. And then we only had one irreducible representation, giving us the least eigenvalue. So everything had to be in like that eigenspace. Okay, and then Spiga, Pablo did this work where he showed that PGL NQ for n greater than 3, I guess, has the EKR module property. And his paper is like beautiful. It's amazing. It's so well written and lovely. And my open question is, how else can we sharpen the ratio bound? What other things could we do to strengthen it? I'm going to partially answer this question with my next one. We can use weighted adjacency matrices in our ratio bound. So if we have a weighted adjacency matrix, we're still taking, it's going to be a symmetric matrix. The rows and columns are indexed by the vertices in the group. But instead of putting 1 or 0, meaning edge, no edge, we put a weight on the edge. So we get the IJ entry non-zero only if, oh, the entry is non-zero. I feel like maybe I wrote this terrible. The idea is that we're putting weights on edges, and that's what we enter in the matrix. And we can put a 0 there if we want. We can throw edges away. And then the ratio bound holds again. So this time the weighting, the D, I guess degree is more like the row sum, and then tau is the eigenvalue over a weighted adjacency matrix. And we can get a lot of improvements by weighting our adjacency matrix rather than just using the 0, 1. Okay, so if we're going to weight a derangement graph, the edges are two elements are adjacent if they form a derangement. The derangements are a union of conjugacy classes. We can put weightings on the entire conjugacy classes rather than the individual elements. And if we have a weighting where we get equality in the ratio bound, then we also have a weighting where we get equality in the ratio bound, but the weighting's constant on the conjugacy classes, because we only care about the eigenvalues. The eigenvalues come from the characters. The characters are constant on a conjugacy class. So if we have a weighting that works, we can take that weighting and average it over the conjugacy class and just use that on the entire conjugacy class. So you don't have to worry about weighting individual guys, just use the conjugacy class. And then the open question is, can we always find a weighting that works for a two-transitive group? So for any two-transitive group, can we always weight the conjugacy classes so that we get equality in the ratio bound? I think, yeah, but I don't know. Okay, this is one of my favorite examples, PSU 3Q. This is like an abbreviated form of the character table. There's 2 families of conjugacy classes of derangements, and I put them in 2 different categories because there's a lot of them and it was kind of hard. And I have the trivial character right here, and I've got a couple sneaky little characters here. What I wanted to do was find a weighting that would give me the right number in the ratio bound. And so what I wanted to do was just weight the family of conjugacy classes. And I wanted to weight it so that these chi1, chi2 both gave me an eigenvalue of -1. And I wanted to have the trivial character give me the right number so I'll get equality in the ratio bound. And amazingly, one exists. Like when I first saw this, it was like an overdetermined linear set of linear equations. And I was like, that's not going to work. It did work. Not only did it work, but a third character also lined up to give me an eigenvalue of -1. So I was able to show that PSU has the EKR module property, and I find it astounding that such a weighting exists, and I don't know why. It felt so magical that it seems like there's got to be something else in play. So Spiga and Tiepp and I, we proved that all two-transitive groups have the EKR property. And we did 2 reductions. First of all, if we have a sharply one-transitive group, we've got the size and we're done, click, co-click bound. And then we also have the trick that if I have a big group and a little group, if the little group has the has the EKR property, the big guy does. So we also use that if we have the subgroup trick. So we only need it to look at minimal transitive subgroups of almost simple type. So we have all the whole world of two transitive groups, bunch of them go away, and then we only need to look at this smaller family. And what happens is these guys are entirely known. So here's my little picture. I'm running out of time, but we'll see how it goes. This list of groups were the only groups we had to check. I've sort of color coded them. The red ones are finite, so I could just get Gap to tell me the answer. The blue ones, I could just use the character table and everything was fine. The purple ones, we had to find a weighting. But just going through, we got them all. But then Peterson and I got the result that I think is the right one. If you're two transitive, then you have the module property. And we sort of did a similar proof. We divided the two transitive into two piles. If you have the minimal normal subgroup, we were able to show that the projection of a maximum co-clique to any module is the same as the projection we'd get with the canonical guys. So we could look at the modules and force ourselves into the right module. And for the other groups, again, that's where we have the finite list. You could go through and show that we only needed to consider the minimal subgroup. And then I just went through the list and checked each one. So one of the open questions here is what other families of groups could have the property? So we've got all the two transitive, not all the one transitives, but like what other big families could have this property? Okay, oh yeah. So once for a two transitive group, the characteristic vector of any maximum intersecting set is a linear combination of the canonical ones. And it's going to have the same inner distribution. So the idea of the inner distribution is if I take a set and I look at which cosets one element times the inverse of the other lies in, it's a certain pattern and it's the same for everybody. So if we're looking at a two transitive group, all the examples I have, the maximum co-cliques are groups or cosets. I don't know, I don't know why that would be. So I don't know if all the maximum guys have to be one of these two. And there's lots of examples that haven't been checked. Can we have a group that is a maximum co-clique that's not isomorphic to the stabilizer of a point? So all the examples I have where it's not the strict EKR property, I'll have a second group that's also the same size and intersecting. They're not conjugate, but they're isomorphic. Like, I don't know. And when does a group have non-conjugate subgroups that give the same induced representation? So when can we have two groups that are not conjugate but still have the same representation? Okay, I have 1 minute left. I'm not sure how many slides I have here. This is just a summary of some of the groups that have the strict EKR property. I haven't really talked about how you can prove the strict EKR property, but that's always a question that you can ask. So for one transitive groups, we never get this handy irreducible representation giving us the right eigenvalue for the ratio bound. So you can ask, when can we put a weight on the conjugacy classes so that the ratio bound will hold with equality? And so what my trick is to set a weighting on the conjugacy classes and then force all of the eigenvalues to be at least -1. And -1 is just a convenient number to use. And then I want to maximize the degree. So I'm trying to get the biggest ratio between the degree and the least eigenvalue. So if I force the least guys to be -1, maximize the largest, the eigenvalue coming from the trivial character, that should give me the best bound. And when can I find such a weighting that's going to work? Okay, so let's see. I don't know which slides are next, but we'll go over these we'll skip some stuff because people want to go on. Oh, the group, the GL2Q, we can do that for this group. There's other proofs that this group, these two authors have a paper showing that this group has the strict EKR property, but you can find weightings that will work for this group. One direction to take the work is to look at your symmetric group with acting on T sets or on ordered T sets. So this is T intersection. And this is an action that is one transitive, but in these papers, Ellis, Friedgut, and People and Ellis proved that you can find a weighting. Now their proof required n to be sufficiently large, but this is an example of one transitive groups where they were able to find a weighting that worked. Okay, I'm gonna skip that. Okay, so there's other properties that people have looked at. Lee, Song, and Pentangi looked at intersecting groups. So instead of asking what's the largest intersecting set in a group, what's the largest intersecting subgroup? And I think that's a good property. Bristani and Malhai-Kari, they were more careful about their groups having the property. They defined a group action to have either the EKR or the strict EKR property. But what they did is they said a group has the EKR property if for every subgroup, the action has the EKR property. And they were able to prove some nice things as well. In terms of open questions, you can always ask for any group, what are the maximum intersecting groups rather than sets? And then which groups have the EKR property or the strict EKR property? And by groups, I mean by their definition. And they're able to show that if any group has the EKR property, so group, any subgroup, any action, it always has the EKR, then your group's going to be solvable, which is sort of surprising, which I thought was nice. Okay, oh, other problems. Okay, this is my last slide. Just some other problems. If we have two transitive groups, we've got this nice vector space that's the span of Vij. What are the other Boolean vectors that are sitting in that vector space? And I think Nathan Lindsay has stuff to say about this. If we're holding on to a one transitive group, what sort of interesting things can happen? And I think Sarah Biddy, Razafima Hatratra, who I think is speaking on Wednesday, has some really interesting things that can happen. And like I'm looking for something really weird where the largest intersecting guys are not anything you'd predict easily. Oh, and another open question. When we look at the groups that have the EKR property, the strict EKR property, it's the stabilizer of a point that's the largest one, which is like not at all closed under conjugation because the elements are very different. What's the largest set of permutations that you can find if you add the condition that it's closed under conjugation or some other property like that? Okay, that's it. I'm sorry I went 3 minutes over.
It's not a problem. So questions, let's start with, there we go.
Yeah.
Oh. Thanks again, Karen.
Clapping on Zoom is weird.
Not just the speakers. So questions. Okay, well, let me start. Let's look at that open question at the bottom there. I don't understand it at all. I mean, you're asking something about a union of quantity classes. Okay, so I just take the everything and I get the entire group. So that's not what you mean. So what?
Okay, yeah. Oh man, I must have been doing this late. Longest of.
That's all right.
Thank you. Intersecting permutations.
Okay. Okay.
Yeah. Yeah. That's not a very interesting question. And there's been some work done on this with sets. So the original EKR theorem was what's the largest collection of intersecting K subsets? And you take all of the subsets that contain one, and that's the biggest. And then the question was, what's the largest if every element has to occur equally often, like the largest regular, maybe, collection of subsets? And you can ask for similar things here.